Hi everyone. So in this video, we're going to learn how to solve exponential equations. So an exponential equation is an equation that looks like this. So it's an equation where the variable is in the exponent. And so we're going to see that there are two main methods for solving exponential equations. And we're going to start with the first one, which I think is in a lot of ways the simpler method, but we'll see that it only works for special types of exponential equations. Okay, so I want you to take a look at this first equation that is written down here, and I want you to think if you can figure out what the solution is. So remember that solving an equation doesn't mean doing algebra tricks. It doesn't mean dividing both sides by something. Solving an equation just means finding the value of x that makes an equation true. So I want you to think, can you figure out what value of x would make this equation true? So this is one that, I think some of you might have been able to do in your head, right? You can look at this and say, well, if x was 4, that would give me what I'm looking for, right? Because what is special about this number 27? Well, 27 is the same as 3 cubed, right? So if you can just kind of look at this and say, well, what power would I need to raise 3 to get 27? That would immediately tell you that this exponent has to be 3, right? And then you could figure out that x is 4. So let me write that down in a slightly more kind of stepped kind of way. So really what we're thinking with this example is that 27, the right-hand side, can be written as 3 cubed. And so what that tells us is that x minus 1 must be equal to 3. Right? Because if the left-hand side is 3 to the x minus 1 and the right-hand side is 3 cubed, then x minus 1 must be 3. And so from here, we can conclude that x is equal to 4. So the way that I would describe this method is basically we're relying on the fact that if you have a left and right-hand side that can both be written as the same number to an exponent, then you can conclude that those two exponents must be equal to each other. So this method we'll see is really only going to be useful when the right-hand side is a nice number, is a number that you can easily see what, how to write it as a power of the base on the left-hand side. So let's look at another example. So 2 to the x plus 4 is equal to 1/8. So just like the last one, this right-hand side can be written as a power of 2, right? 1/8 is 2 to the negative 3. So x plus 4 has to be equal to negative 3 in order to make this equation true. So x plus 4 is equal to negative 3. That would tell us that x is equal to negative 7. And you could check your answer, right? If you took negative 7 and plugged it into our original exponent, you would have negative 7 plus 4, which is negative 3, and 2 to the negative 3 is equal to 1/8. All right, one more example with this method. So this one is 5 to the 2x minus 3 is equal to 0. So this one is a little bit different, right? I would say it's actually a lot different because there's no way to write the right-hand side as a power of 5, right? Like try as hard as you can. You're not going to be able to come up with a number that you can raise 5 to and get 0. You might guess 0, but 5 to the 0 is actually equal to 1, right? So that doesn't work. So what does that tell us? If there's no way of writing the right-hand side as 5 to a power, what does that mean about this equation? Well, it means that the equation has no solution, right? Because again, solving an equation is just finding the values of x that make the equation true. And if there's no exponent that we can raise 5 to get 0, that means there's no value of x that makes it true. So there's no solution. Because there is no power we can raise 5 to and get 0. And by the way, it doesn't even really matter what this exponent is, right? This could have been really any kind of expression involving x, and the answer is the same. No matter what that exponent looks like, we just know that it can't exist in a way that would give us a 0 on the right-hand side. So no solution. Okay, so like I said, the kind of drawback of this method is that it only works if you really can write your equation like this. So I want to look at an example that is actually very similar to this first example, but the slight difference in it will force us to use a different method. So let's look at another example. So now we have 3 to the x minus 1, instead of being equal to 27, is equal to 26. So although those two equations are very similar, the difference with this one is we cannot, or at least I cannot, just look at this and think exactly what is the number I need to raise 3 to get 26, right? Because it's not going to be a whole number. It's not going to be a nice friendly number. And so what are we kind of left with? Like what method can we use here? Well, the issue with an exponential equation, the thing that makes it different from other equations is the fact that the variable is stuck in the exponent, right? We don't, like, when our variable is in the exponent, we can't really do anything to it. You can't, if, like, let's say you thought you could add 1 to both sides of this equation, that would work, but that would give you 3 to the x minus 1 plus 1 is equal to 27, and that doesn't really help you. Yeah, I guess when I say it would work, I mean it would be valid. You can do anything you want to both sides of the equation, but that doesn't mean that it's useful. So what I'm getting at here is that you can't, if you try to add 1 or multiply both sides, divide both sides, that's never going to be affecting the exponent. That's going to be affecting, like, down here. And so in order to be able to isolate x, we need to figure out a way to get the x out of the exponent. So we have to think about what is something that we learned recently that allows us to take an exponent and kind of bring it down. Well, remember we learned a logarithm rule, right? We learned that if you take a logarithm of a number to a power, that is the same as bringing that power down. And so the second method that we're going to use is that we're going to take ln or log, it doesn't matter which one. And technically you could even use a different type of logarithm, but because ultimately we're going to be typing stuff into our calculator, you want to use ln or log because those are the ones that your calculator has a button for. So we're going to take ln or log of both sides of the equation. And then we're going to use a logarithm rule. So the logarithm law, which tells us that if you're taking a logarithm with any base of a number raised to a power, that's going to be the same thing as bringing that power down and multiplying it with the logarithm. Okay, so let's see how that plays out in this example. So I prefer ln, as I mentioned. I don't really know why, but I'm going to take ln of both sides. So we have ln of 3 to the x minus 1 is equal to ln of 26. Okay, so based on that rule that we wrote down above, we can take this x minus 1 and bring it down. Now, the important thing to remember is that when you do that, you need to put parentheses around that exponent because it's getting, the entirety of the exponent is getting multiplied with the logarithm. Okay, so this might look like kind of a crazy equation to you right now, but what I want you to keep in mind is that ln of 3 and ln of 26, these are just numbers, right? They're numbers. If you type them into your calculator, you can even get an approximation for what they are. However, and we'll talk about this a little bit more a little later, you don't want to type them into your calculator right away because there's this difference, right, between exact and approximate form. And so a number like ln of 3 or ln of 26, those are not going to be nice, clean numbers. So as soon as you type them into a calculator, you're going to lose some accuracy. So you don't want to do that until the very, very end of the problem. But yeah, basically, I just don't want you to be intimidated when you look at this because I want you to just remember that ln of 3 and ln of 26, they're numbers. They're numbers that are written in a funny way, but they're just numbers. So there's a couple of different ways you could go from here, but the easiest thing to do would be to divide both sides by ln of 3. Because the x minus 1 is already kind of factored out on its own, you might as well just divide both sides by ln of 3. If you really wanted to, you could also distribute. You could do ln of 3 times x and ln of 3 times negative 1. And that would just kind of give you a slightly messier looking but equivalent answer. So I would just divide both sides by ln of 3 instead. So that would give us x minus 1 is equal to ln of 26 divided by ln of 3. So our goal again is to solve for x. So we want to isolate x, so we can do that by adding 1 to both sides. And so that would give us ln of 26 over ln of 3 plus 1. And you might look at that and think it doesn't look like it's done, like it doesn't look like it's an answer. It looks like there's still something to solve, but this is your answer. This is in exact form. So as we said, ln of 26 and ln of 3, those are numbers. So this is a number. Your answer is a number. You're done. We've isolated x, and the right-hand side is just numbers. Now, in many cases, you'll also want to know the approximate value of your solution. And so you want to do that by just typing this expression into your calculator. And so this is why you want to wait until the very end, because you want to be able to write your answer in exact form. And then once it's in exact form, you can just type that all into your calculator all in one go. And so if you type in ln of 26 over ln of 3 plus 1, that is going to give you approximately, I think, 3.97. So this is an approximation. But the reason that the approximate answer is kind of, I think, valuable is it can help you kind of make sure that your answer makes sense. So just to remind you, in our first example we did, we had this very similar equation. We got x is equal to 4, right? And so in this equation, the right-hand side was 26 instead of 27, and we got 3.97 approximately. And so that feels like it makes sense, right? Because our answer should be close to what we got on the first one, and it should be a little bit smaller because the right-hand side is smaller. And I just want to quickly make a note so that if anyone's just reading these notes, they see this, that you don't want to type these into your calculator until the last step. And as I mentioned, there's basically two reasons for this. One is that you want to be able to write down your exact form. And then the other one is that the earlier in the process you make an approximation, the more potential there is for the approximation to kind of get further and further off. So for example, if you typed in ln of 3 and ln of 26 at this step, then when you go and divide those in the next step, that would make your answer even further off than it would be if you were to type them in all at once at the end. So just keep those numbers all kind of with you until the very end. Okay, so I want to now talk about solving equations that have kind of one or two more additional steps at the beginning. So the important thing that we need to know is that anytime you're solving an exponential equation, you want to start by isolating the exponential part of the equation. So what do I mean by that? Well, this equation here, notice that it has some extra stuff going on, right? It has this plus 1, it has this multiplication by 3. We want to get this equation to look like e to the x plus 2 is equal to something. And then we can proceed with the method that we just learned. So how can we do that? Well, we can start by subtracting 1 from both sides. So if we subtract 1 from both sides, we get 3e to the x plus 2 is equal to 9. And then we can just divide both sides by 3. So that would give us e to the x plus 2 is equal to 3. So now we're in a position where we can apply the method that we just learned. So we can take a logarithm of both sides. Now I mentioned how either ln or log will work, and that is true. You can always use either ln or log. If your base is e, you should use ln. And the reason for that is that it will allow you to write your answer in a simpler way. Nothing would be wrong if you used log, but it just would make your answer look more complicated than it really has to be. So if we take ln of both sides, what is the advantage of that? Well, we can bring down the exponent, but you can bring down the exponent no matter what logarithm you're using. But the advantage comes in on this step. So ln of e is just equal to 1, right? ln of e is asking what power you have to raise e to get e. The answer is 1. And so that means that our equation can be simplified even further, right? We can just write it as x plus 2 is equal to ln of 3. And so that's a rule that we mentioned in an earlier video, where if you have ln of e to a power, it's always just going to simplify to what that power was, because the ln part is going to go away. And let me just actually scooch this down a teeny bit. Okay, so from here, we can subtract 2 from both sides. And that would be our exact answer, right? So this is the exact form. And then if you wanted to approximate, you could type into your calculator ln of 3 minus 2, and it looks like that is approximately negative 0.90. So that is our approximate. So before we move on to our next example, I just want to point out kind of how you could go wrong on this problem. So I mentioned how you really want to always isolate the exponential part of the equation before doing any of the next steps. So let's say that you didn't. Let's say that you decided to, from the get-go, take ln of both sides. So you said ln of 3 e to the x plus 2 plus 1 is equal to ln of 10. So technically there's nothing wrong with doing that. Like, you can always take a logarithm of both sides of any equation and you'll still have a valid equation. However, remember that the whole point of taking a logarithm is so that we can basically access this exponent, right? So that we can bring it down. The problem is that if you take ln of all of this stuff, there's no way to break this down. Right? We learned that when you are using logarithm rules, there just isn't a way to take a logarithm of a sum and break it down. So long story short, this method just wouldn't get you anywhere. If you tried to take the ln of both sides too early, it just wouldn't be useful. And so you don't want to do this. You want to start by isolating your exponential part, because then when you take the logarithm, you can right away bring that power down, and yeah, you'll be able to actually access that exponent. Okay, I want to look at a couple more examples. So this next example, we have 3 times 2 to the x minus 5 minus 7 is equal to negative 4. So one thing I just want to point out right away, remember that you cannot just multiply these two numbers together. It just doesn't work that way. So you cannot write this as 6 to the x minus 5. That would not be the same equation. So instead what we want to do is start by isolating the exponential part. So let's start by adding 7 to both sides. So that would give us 3 times 2 to the x minus 5 is equal to negative 4 plus 7 is going to give us 3. Okay, so now we can divide both sides by 3, and we get 2 to the x minus 5 is equal to 1. And so this one you could do logarithms. So maybe one thing I should mention is that, we have these two methods. You can always use the second method. Taking ln of both sides will always work. However, there's a lot of cases where it is not the easiest way. So if you can look at the right-hand side of your equation and see it as a power of your left-hand base, then method 1 will always be the faster and easier way. If you can't, that's where the second method is better. But if you just are kind of struggling, you can always fall back on the second method. So in this case, you might not see it right away, but we can write 1 as a power of 2, right? 1 is 2 to the 0. So we can rewrite this as 2 to the x minus 5 is equal to 2 to the 0. And so now this tells us that x minus 5 has to be equal to 0. And so in this case, we get a nice clean answer that x is equal to 5. All right, I want to do one more example, and I guess I forgot to write it down here, so let me just write it down. So last example, not the last example of the video, but the last example kind of in this same vein. So we have 5 times 2 to the 3x plus 1 is equal to 30. So first thing we want to do is, again, isolate the exponential part. So we want to divide both sides by 5. So we get 2 to the 3x plus 1 is equal to 6. Then, as we've been doing, we want to take a logarithm of both sides. So we have ln of 2 to the 3x plus 1 is equal to ln of 6. Then we can take this exponent and bring it down and say 3x plus 1 times ln of 2 is equal to ln of 6. And so just like we did in the first example on this, with this method, we want to divide both sides by ln of 2. So that will leave us with 3x plus 1 is equal to ln of 6 over ln of 2. So now our goal is to isolate x, so we can subtract 1 from both sides. So we get 3x is equal to ln of 6 over ln of 2 minus 1. And then from here, we have to divide both sides by 3. I think in order to make our answer kind of look nicer, instead of thinking of it as dividing both sides by 3, think of it as multiplying both sides by 1/3. So if we multiply both sides by 1/3, that's going to give us ln of 6 over 3 times ln of 2, right? Because if you multiply by 1/3, you would get that extra 3 in the denominator, and then that would be minus 1/3. So this would be our exact form of our answer. And then the approximation, if you type all of that into a calculator, you should find that x is approximately equal to 0.53. So there's a reason I wanted to show you this, this last example, which is that there is a different way you could do this. So when I said at the top of the page that you always have to isolate the exponential part first, that's not always the case. So if you have something like this where there's nothing being added, so notice that this is different from this example or this example. In the first two examples, we were multiplying our exponential and then we were adding or subtracting to it. This one is just multiplying. And so you actually can, if you want, take a logarithm of both sides right off the bat. I want to show you what that looks like. We'll see that it's a little more complicated. So I still think it's better to isolate the exponential part first, but I just want to, I want to make sure I'm being honest with you. This one you actually could take the logarithm right off the bat. So what would this look like if we took the logarithm right off the bat? Well, in this case, we actually can use the logarithm rule to break up the left-hand side, right? So the reason that I told you that we had to isolate first was in this first example when we were adding, that made us get stuck when we took the logarithm. But in this example, because we're not adding or subtracting anything from the logarithm, we actually can use logarithm rules to break this up. Right? So there's a logarithm rule that lets us take multiplication and break it up into addition. Okay, so where would we go from here? Well, now we can still use that same exponent rule. So we could bring the 3x plus 1 down, and I'm just going to kind of rearrange the order of this. So I'm going to rewrite this as 3x plus 1 times ln of 2 plus ln of 5 is equal to ln of 30. And I'm not going to keep going with this, but basically if you were to subtract ln of 5 from both sides and then divide both sides by ln of 2, at the end of the day, you would get the same answer. So if you're interested, I would encourage you to see this through and see what happens, and you'll see that you get the same answer. But it's a little bit more work. So I just want to show you that you could technically do it this way, but I still think it's better to isolate the answer. So I'll just write down, you would get the same answer but it's more work. Okay, so the last thing I want to talk about in this video is going to be a little bit different. I want to look at some examples of equations that where we're going to solve actually by factoring. And so in these, we're going to be factoring, and we're going to be factoring with both factors that are exponential and factors that are polynomial. Okay, so I want to take a look at this equation. So why are we talking about factoring in this context? Well, factoring is useful when you have an equation equal to 0. So why is that the case? Well, remember that when you have an equation equal to 0, if you can factor it, then you can say that one of the two factors has to equal 0. That doesn't work with other numbers, right? It's not true that if you have something like a times b is equal to 6, you can't be like, well, a is 6 or b is 6. It is true that if you have something like a times b is equal to 0, that a has to be 0 or b has to be 0. So it's a special thing about equations that are equal to 0 that makes factoring the right approach for them. Okay, so what can we factor out from this? So let's start by seeing what is a common factor that both of these both of these terms have. Well, they both have an e to the x in them, right? So let's start by factoring out an e to the x. So what are we left with when we factor out e to the x? Well, we have x squared minus 5x. And then we can actually go a little bit further, right? So notice that the part that is still in the parentheses, that actually still has a common factor of x. So we can pull out another factor of x. So we can now rewrite this as e to the x times x minus 5 is equal to 0. So now we have three things being multiplied together and we're getting 0. And so what does that tell us? That tells us that one of those three things has to be 0, right? That's how solving by factoring works. So our options are e to the x is equal to 0, x is equal to 0, and x minus 5 is equal to 0. So e to the x is equal to 0. Let's pause and think about that for a second. Can you think of any value of x that would work to be a solution to that part? No, right? There's no value of x that makes this true. This came up earlier in the video. For any number, any non-zero number, you can never raise it to an exponent and get 0. It's just not going to work. E to the 0 is 1, so there's just no option that would give us 0. And so that tells us that this part gives us no solution. Now, I want to be clear that that does not mean that the whole equation has no solution. It just means that the solutions are not going to come from this part being 0. So that really tells us that in order for this equation to be true, we're going to rely on one of these two factors being 0. This is not going to be the factor that gives us the solution. But that doesn't mean that, we give up and say there's no solution. That means that either x is 0 or x is equal to 5. So by the way, if you were to graph the function, so let's say you took this and set it equal to f of x and graphed it in Desmos, you would see that it has two x-intercepts. It has an x-intercept at 0 and at 5. So I would encourage you to look at that. Take a look at what that graph looks like. This isn't really a function that we've seen before. It's kind of blending together x's and e to the x's. So you probably don't really know what shape it's going to look like. But you do know that it's going to have x-intercepts at 0 and 5. Okay, so one other example, pretty similar. So we have 3x squared times e to the x minus 9x squared is equal to 0. So in this case, we do not have a common factor of e to the x in both of them, right? There's only an e to the x in one of them. What is the common factor? What goes into both of these terms? Well, they both have a factor of 3x squared. So let's factor out a 3x squared. So if we factor out 3x squared, we're left with e to the x minus 3. So just like in the last example, when we have multiple factors being multiplied together equaling 0, that tells us that each factor could equal 0. And that, at least one of the factors has to equal 0 to give us our solution. Okay, so first one is 3x squared is equal to 0. So that's the same thing as saying that x squared is equal to 0. And that's the same thing as saying x is equal to 0. So that is one possible solution. So what about this one? E to the x minus 3 is equal to 0. So this one we're going to have to actually go back to the methods that we were talking about on the last page. So we want to start by isolating the exponential part. So that would mean e to the x is equal to 3. And then we want to take a logarithm of both sides. So in this case, we can take ln, and this we'll see is easier than the examples we did on the previous page, because ln of e to the x is just x. You could write it as x times ln of e, but remember, ln of e is just 1. So a good thing to be familiar with, and we talked about this in an earlier video, is again, anytime you're taking ln of e to a power, it's just going to simplify to whatever that power was. So in this case, we're just left with x is equal to ln of 3. And if you wanted to approximate that, that would be approximately equal to 1.10. So again, I would encourage you with this example just to kind of see what it looks like. Take this expression and set it equal to f of x and graph it in Desmos. And what you should see is that you should have an x-intercept at 0 and another one at approximately 1.10. All right, so that is it for this video. In our next video, we're going to be talking about solving logarithmic equations. So equations where instead of the variable being within an exponent, the variable is within a logarithm. So I'll see you on the next video.